Today we will cover chapter 8 and its principal stresses under given a loading. So just to summarize what did so far is, in chapters 1 and 2 we learned how to determine normal stresses due to loads, and in chapter 3 we analyze the circular members due to torsion and we find our shearing stresses. In chapter 4 we find the stresses due to bending. In chapters 5 and 6 we find the shearing stresses due to transverse loads, and also we determine how to find the shear and moment diagrams throughout the beams. And in chapter 7 we learn that if you determine stresses in one coordinate system, we can find what are our maximum stresses, normal stresses and maximum shearing stresses. And in chapter 8 what we will do is basically we will combine all the things we have learned and we will analyze the members when we applied couple of different loads, and we will find the stresses in given axis system, and then we will find what are the maximum normal stresses and also what are the maximum shearing stresses. So just to kind of summarize what we did is, if you have a beam and you can apply a point load, and plus you can also apply some distributed load, and whenever you cut it, what we will get is, for example in this case, when you cut it you will get a shear force V and you will get a moment. And if you know a moment, then I can get my normal stress at any point, which is equal to minus My over I, and you can get your shear stress by using minus Vq over It. So these are the things we learned. And what I know is, for example in this case my maximum normal stress will happen at the ends, so at the top side or bottom side, and my maximum stress is MC over I. Okay, but for shear, so my maximum stress occurs at the neutral axis and it's equal to Vq over It. So you just need to find the Q over this area and then It. So here on top surface I have maximum stress due to bending, and it does not create any normal stress when y is equal to 0. But at this point I have my maximum shear, and if you look at any point in between, what you will find is you will have a normal stress, which you can calculate its value by using this equation, plus you will have a shear stress, which you can calculate its value here. And after this, what I can do is, next on chapter 7 we learned that at each point, as long as I know my normal stress and shear stress, I can find what's my maximum stresses. And if you look at there, so this is how it will look like. For example here I only have shear, but I know that if you rotate it 45 degrees you will get this maximum and minimum values, and at any other point you just need to rotate, and here since I don't have any shear, this is already my maximum. So at any point along this beam you can find what is your maximum. Okay, and depending on the values of your normal stress and shear stress, this maximum value, it might be something different than the sigma m, which you might get your maximum from there. Okay, so the question is, can the maximum normal stress within the cross region can be larger than this value? Okay, and just an example to look at here is, for example this is another beam, and you just apply one load at the end, and whenever you cut it at different x values, so for example here you cut it in x is equal to 2c, and here you cut it x is equal to 8c. Okay, and whenever you cut it, and if you look at your stress profile at different values, for example this is when y is equal to 0, so at the midplane. Okay, so you only have shear, so this is why you need to rotate different angles, and then what happens is, if you increase this x, for example if you increase x from 2c to 8c, the moment increases. So your shear force is same everywhere, which is equal to P, but your moment is equal to P times x, so your moment increases. Okay, and then this is why when you look at here, for example at when y is equal to 0, here when you find your maximum, it's equal to 0.25 of your sigma m, which is MC over I. But when you increase that value, x is equal to 8, this becomes smaller because the moment becomes more dominant and the shear stress becomes less dominant. But the important thing here is, when you look at them, you will see that these numbers, they're all changing. So depending on your location, so you will find that your maximum stresses will change. Okay, and in this case we will not gonna get it. So your maximum value will never be larger than sigma m. Okay, but for some other more complicated cases, it might be. And this is an example. So for example, if you have this I-beam, and if you look at there, so normally I know that my maximum normal stress due to moment is equal to MC over I, and it will happen at A or E, and your maximum shear stress will occur at in the middle at point C. So the problem is when you look at point B, okay, so B is kind of close to A, so it has still a large normal stress, and also it also has a large shear stress because the thickness here is changing, is small. So which means that at this point B, so you might have a large shear stress, and your normal stress is also large. It's very close to this value. So which means that when you actually find your sigma max at point B, it might be even greater than sigma m. So there's a possibility. So which means that when you check your maximum stresses, you need to look at not only point A, but you also need to consider point B. And depending on the design of your cross section, there might be also other important critical points that you need to look at it. And what we will do is, actually we will show an example to show how your sigma max might be different. Okay, so in this case I have a 160 kN force applied to W252 rolled steel beam. So which means that I know the information about cross section, I know its I know its area, and etc. And they say that the normal stress should be less than 150 megapascal at this section AA prime. So when you cut it here, your normal stress should not exceed 150 megapascal. So what I need to do is, first I need to determine my shear and bending in section A to A prime, and then I will find my normal stress. Okay, and my critical points will be on the top and also the connection of flange and web, and then I will find my shear stress there at the flange and web junction, and I will find my principal stress and see if it is larger than the stress at the top surface. Okay, so first thing is, if you cut it, so since the location is given, I can just put my I can just find these values. Okay, and when you find them, so you find that your moment is equal to 60 kilonewton and your shear is equal to 160 kilonewton. Okay, and your shear goes up because this one goes down, and since this creates a clockwise moment, your MA is counterclockwise. Okay, and you just find the value. So what you know is on top you will have tension, on bottom you will have compression, and then you can look at the geometry, and this is what you can get from the appendix. So this is the beam, how it looks like. The I is given, the S is given, and all the dimensions are given. Okay, and what I know is, I know that if you find your normal stress, so it will be 0 at the neutral axis and it will increase linearly. Okay, and the maximum will be at point A, and you can also find your stress at point B. Okay, and so just due to moment, I can find what's my stress at A at the top, and the way we find it is, so at sigma A is equal to moment divided by S. Okay, so the moment is 60 and S is given from the geometry, so you find your sigma A, and since it's linearly changing, so if you want to find what's your normal stress at point B, I can use this equation. So my normal stress at B is equal to my normal stress due to moment at A times YB over C, and YB is the distance from C to B. And if you just plug the numbers, you can get that my sigma B is equal to 102.9. And as you can see, so my maximum normal stress due to moment is 117.2, and at point B it's equal to 102.9. So they're not that different. So this is why this point is critical. Okay, so normal stresses, we can find them. And then next is, so I need to also find, since I also have this shear VA, I need to also find my shear stress. Okay, and again, if you look at it, this is the geometry, and what I want to do is I want to find my shear stress. So how do you find our shear stress? Is I will use my equation VQ over IT, and I is given in the previous slide. So I is given here. So I know the I of my cross section. Okay. So it's the I of whole cross section, moment of inertia of the whole cross section. And what I need is I need Q. So in order to find Q, I need to find this area, okay, above B, and I need to find Q of that area with respect to my C. Okay. And if you do that, so Q, so I need to find this area, which is equal to, so it's a little bit different, but this is should be, I guess, 206 times 12.6. Okay. And then the distance from the centroid of that area to C is 96.8. So if you do that, this is your Q. Okay. And then if you find your shear, is equal to the shear force times Q divided by I and T. So I is already given, and the T is the thickness of the web. So if you do that, this will be your shear stress. Okay. And as you can see, it's quite large. So this is not the maximum shear stress, so your maximum shear stress will be at C, but if you find your shear stress at point B by using VQ over IT, you end up with 95.5. So as you can see, this is also a very large number. Okay, and then, so which means that at point B, I know what's my normal stress due to moment, I know what's my shear stress due to shear force, so which means that I can find my principal stresses at the junction at point B. Okay. And it's equal to basically my average, which is 1/2 times my normal stress at B, plus, so it's normally 1/2 times sigma B minus sigma Y, but I don't have any stress on the Y axis, so it's basically just this one, times the shear square. So if you do that, what you will end up is, you will find that your maximum stress is equal to 159.9. Okay, so the normal stress due to bending was 102.9, but since I also have a large shear stress, now if you calculate your maximum stress, it ends up with almost 160 megapascal. And since it's larger than 150 megapascal, I know that this cross section will not work. Okay, and just for comparison again, so at point A, what we get is at point 8, your maximum normal stress due to bending was 117.2 megapascal, but at point B, what I get is my maximum stress is about 160 megapascal. So which means that if you load it, so at point B, your stress will be more than 150 megapascal, more than your allowable stress. So this design will fail. Okay, it will not fail at point A, but it will fail at point B. Okay, and this is due to this large shear stress. So you have normal stress due to moment, but you also have a large shear stress. So the combined effect of your normal stress and your shear stress, it creates a larger maximum normal stress. Okay. All right. So this is just an example, and it shows that. So when we are looking at the beams, especially if your cross section is not constant, the thickness is changing, there might be cases where you need to look at different points. Okay, so for this beam, for example, A is critical because you have a maximum normal stress. C, it might be also critical because you will have the maximum shear stress there due to shear force. And B is critical because you have normal stress and you have shear stress. And at point B, you have a large normal stress and large shear stress. So this is why point B is critical. At point A, you have only normal stress, no shear stress. So, and at point C, you only have shear stress, no normal stress. So depending on their relative values, you might need to check all these points. Okay. So we will solve also one more example on this topic. So again, we have a beam, and now we have a point load, plus we have this distributed load. And what it tells us is, so the allowable normal stress is 24 ksi, and the allowable shear stress is 12.5 ksi. So we want to select a wide flange beam, which should be used. So in this type of question, what we need to do is, first we need to draw our shear and moment diagrams because I don't know which point to look. In the previous question they asked us, they told us, look at this section. But in this case, in this beam, I don't know which section should I look at. So this is why first I need to draw my shear and moment diagrams. And in order to do it, first I will determine my reactions at A and D. And then I will determine my shear and bending diagrams. And I will look at these critical points where I might have a maximum shear and maximum moment. And then after I select the where should I look, then I will look at the I will calculate a section modulus, and then I will find the maximum normal stresses and see it will satisfy the requirements. Okay. All right. So the first thing is I need to determine my reactions. Okay. And again, I'm not going to go into details, but you can take a moment at A, and then you can find D, and then you can take a moment at D, and you can find your A. But if you do that, these are your reactions. Okay. And then I need to draw my shear and moment diagrams. So here I have 45 kips. So I know that if you draw your shear diagram, it will be a jump. And then I have constant distributed load, so I can find this area. And then my shear will decrease. So it will decrease from 41 to 12.2. So you just need to find the area under this curve. And then here I apply 20 kips, so there will be a jump downward by 20 kips. And then again I have a constant load, so it will just keep decreasing. And at this point I have load D, so it will jump up and then it will decrease. So you need to be able to draw this. And then after you draw this, so I can find all the areas. Okay. And when you find the areas, so here I have positive, here negative, and on this one is positive. So if you draw it, so it will increase, okay, up to this point. And after C, it will decrease. And after D, it will increase to 0. So I will start from 0 and I will end up with 0. Okay. And after I look at this, now I need to look where my maximum stresses might be. And the critical points is, for example, if I look at here, so where is my maximum shear stress? So this point is critical because here I have a large shear, okay, and I also have a moment. So this point might be critical, okay, at point D, just on the left side. And also this point. So here I have my maximum moment, and I need to also find, I see that there is also shear. So again, I will look at the left because it has a larger shear, okay. So the left of C and the left of D, they might be the critical points, okay. And when I compare, so this is very large value and this is very low. So this is why when you look at it, so I can say that, so at this point on the left, my maximum normal is stress normal, my maximum moment is almost 240 kip inches, and I have a shear force. And on this point, basically I also have 43 kips, but my moment is low, so you can also add your moment. Okay. Right. And then what I will do is I will just try to find my I will also try to find a cross section which might work. And when I look at this one, so here, since I have a very large moment, about 240 kip inch, so I need to determine what's the minimum section modulus that I can have. And since the allowable stress is given, I can use this equation. So Smin is equal to my maximum moment divided by the allowable stress. So if you do that, so I need to select a beam which at least a section, at least a section modulus of 119.7. Okay, and ideally, so what you need to do is, so you need to look at all the points. Okay, but and you can do it if you use finite element method. But in this class we are not using, so we need to start somewhere. So what we start is, we say that, okay, let's design it according to this point C, okay, and then let's check it if it works everywhere else. So this is why I will start at this point, since my section module is not given. So I find that if I only consider this moment, and again I didn't consider my shear yet, so if I only design it according to my normal stress, so this is the minimum section modulus I need to have, okay. And if you look at the appendix, you have many options, okay. These are all the beams, which is section modules of at least 120 inch cube. Okay, and when you select it, again I look at this second number, and then I select the lowest one because this will be the most economical one. So from here I want to say that, okay, I want to select this beam. Let's start with this beam and let's see if it works or not. Okay, after you select it, then you can go back to the appendix and you can see the properties of the section. Okay, so the S is given, so the area of the web is given, the thickness, the diameter, everything is given. Okay, so what I want to do is next, so I know that this will be satisfied with my normal stress, and I want to see if it is also will satisfy my shearing stress requirement. Okay, and in this time what we will do is first we will use this approximation. Okay, so this is not exact value, but it is a good approximation to find our shear stress, since in this beams most of the shear stress is carried by the web region. Okay, what I can do is I can kind of approximate it, so I can say that my maximum shear stress is equal to the maximum shear force divided by the area of the web. So again, this is an approximation and we are assuming a uniform shearing stress. Okay, and if you do that, so we find that our maximum shearing force is 43 kips, and you can find the area, and if you find that your shear stress is about 5 ksi. Okay, and our allowable shear stress was 14.5, and as you can see the difference is large. So this is why I can kind of safely assume that my shear stress will not be a problem. So if you just have shear stress, it will not reach to this 14.5 because the approximation you end up with 5. Okay, but if this number was very close to 14.5, I couldn't use this approximation. I need to use VQ over IT. Okay, so this is why I'm assuming that it will work just when you apply your shear. Okay, but now what I need to consider is at this point, okay, I have my maximum moment, but I also have a shear force. This is why I need to make sure that this selected beam, it will survive when you also have this shear force. All right, so this is why what I will do is I will look at different points, and again, since this is I-beam and we did an example before, I know that point A and B are the critical ones. So this is why at point A, I will find my normal stress, which is equal to Mmax divided by S. Okay, and you can just put the numbers, and my maximum normal stress will be equal to 22.6 ksi. Okay, and I don't have any shear because it's the top surface. And then I will look at point B, and point B I can find my normal stress by using this equation since it's linearly changing. Okay, I know the location of YB, so from here I can write that my normal stress at B is equal to my normal stress A times the Y of B divided by the C. And if you do that, you will find that your normal stress is equal to 21.3 ksi. Okay, and then again at point B, I will find my shear stress by using this equation. And again, this is approximation, but it gives very fairly good number. So it's equal to my V divided by the area of web. So I will get 1.45 ksi. Okay. And so at point A, I only have normal stress, but at point B, I have normal stress of 21.3 plus I have this shear stress. So this is why I need to find what's my maximum at point B. And if you calculate it, you will end up with, so your maximum stress at point B is 21.4. And since it's less than 24 ksi, which is our allowable normal stress, so at point B is also safe. Okay, and A was already safe because this is how I designed my cross section. Okay, so which means that for this question, we look at two critical points. Okay, so we look at here on the left side where I have a large moment and I have a shear stress, and we also look at this point D where I have a large shear stress and a low moment. Okay, and so we say that okay, we will design it according to point C, and first we only design it by using a moment. Okay, and then we checked if I selected this beam whether it will be safe on other points, And when we do that, we find that it will be also safe at point B, at that cross section. And if we only have our shear force, it will be also safe because we only end up with maximum shear stress of 5 ksi, and our allowable shear stress is 14.5. Okay, and again, if you want to check all the points, so what you need to do is basically you need to use finite element method so that you can look at whole cross section at all the points. But for us in this class, what we need to do is we need to determine the critical points and then design it accordingly. So a very important topic in chapter 8 is stresses under combined loadings. And in this one, what we will do is basically we'll combine all the information we have learned so far. So what we will do is we will look at different members, and in these members there will be some applied loads, and there might be also some even moments and torsion. And what we want to determine is we want to determine the stresses in slender structure members subjected to arbitrary loadings. So for example, you want to know what are your stresses at point H or K. So in order to do this, first what we need to do is we need to cut where these points are. So when you cut it, okay, so this is my cross section, and what I need to do is this has to be in equilibrium. So which means that I need to find force coupled system at the centroid to maintain equilibrium. Okay, so which means that either you can write your equilibrium equations on this side, or when you have these forces, you can carry these forces to the centroid and also their effect. But when you do that, so what you will end up with is, so you will end up with three forces. You will end up with, for example, in this case, you will have Fx, Fy, and Fc, and you will also have Mx, My, and Mz. So you will have three forces, and you will have three moments. And it's important to identify which forces create what kind of stresses. Okay, so this is why when we group them, so we will group like this. So I know that, for example, in this case, if this is my x-axis, I know that my normal force, my moment along y direction, and my moment along z direction, they create normal stresses. Okay, so again, your normal force, your moment along y, and your moment along z, they create normal stresses, which is shown there at, for example, these 2 points. Okay, and for example, if you have this normal force, I know that I can find my normal stress by P over A. But if you use My, it's important which point you look, because you will use My times Z divided by Iy, and location is important. Okay, and then also we might have a shear force along y direction, we might have a shear force along z direction, plus we might have a torsion. And this shear forces, they create shear stresses, and torsion, it also creates a shear stress. So basically these three, they will create normal stress, and this three, they will create shear stresses. So which means that at each point I need to determine what are my shear forces and shear stresses. And it's also important the directions. Okay, for example, in this case, if you look at Vy, okay, so your shear stress at K due to this Vy will be going upward, but for example, your shear stress due to torsion, it might go downward. So it's important that you look at the direction of each forces and as well as torsion, and determine the direction of your shear stresses. You might need to add them up, or you need to subtract them, and you might need to do other things. So it's very important. Same thing here. So you might have compression or tension, and you need to look at each moment, okay, or your normal force to determine whether you have compressive or tensile normal stress. Okay, and then, for example, at each point, then what we will have is you will have your sigma x, and you will also have your shear. Okay. But what I know is if I have my normal stress and my shear stress, my maximum stress is not equal to sigma x. I need to rotate this element, okay? And when I rotate it, then I can find my principal stresses. Same thing at point H, or same thing with point K, okay? And here, due to our selection of the directions, for example, at point H, I have tau xz because this direction is z. But here I have tau xy. So the indices of shear might change. But at the end, what I need to know is if you have normal stress and if you have shear stress, you need to find your maximum stress. Okay. So our normal and shearing stresses are used to determine the principal stresses, maximum shearing stress, and orientation if it's asked. Okay. All right. So what we will do is we will solve a lot of examples to understand how to deal with these combined loadings. But this is a very important topic. So for the exam, you need to know this very well. For sure, I will ask something from this topic. So this is a sample problem. So what we have is we have three forces applied at point A, at point B, and point D. Okay, so all the dimensions are given. And we want to determine the principal stresses, principal planes, and the maximum shearing stress at point H. So H is there. So the location is given. Okay, and I need to find what are my basically maximum stresses at point H. Okay, so again, in this question, the first thing is you need to cut through the section which point H is there. So I need to cut it at this AFG plane, okay, and then I need to move all these forces to the centroid, okay, and after I move all the forces there, I need to find my normal stress at H, and I need to find my shearing stress at H, and then I will calculate my principal stresses. Okay, all right. So the first thing is I need to find my forces. Okay. How do I do that? So what I will do is at any point whenever I cut, I will have three forces and I will have this three moments. Okay, and I like writing this because you might select different axis system. For example, in this case, X is this way, Y is this way, and Z goes that way, but they might change a lot. So what I do is first I write all fx, fy, fc, and same thing with mx, my, and mz. Okay, and then I determine what is my normal direction. So in this case, this is the plane that you will cut, which means that your normal direction is your y direction. Okay, which means that, so basically you will have a P, so you will have this normal force. It can be tension or compression. And then if you have forces along X and Z, they will be your shear forces. Okay, so I identified. So Fy, I will have normal force, which will create normal stress. But Fx and Fz, they will be my shear forces, and they can only create my shear stress. And on this line, again, I will do the same thing since this is my normal axis. So if you have a moment along Y direction, it will be your torsion. Okay, and on Mx and Mz, they will be your moment. So torsion creates shear stress, and Mx and Mz, they create normal stresses. Okay, and generally forces are easy because you just move them. Okay, so it's easy to find the forces, but moment is a little bit difficult. So one thing is you can do, you can look at all the forces separately and you can determine what they create. For example, if you look at this force 30 kilonewton, okay, if you use your right hand rule and if you put your four fingers around this direction, okay, and if you rotate, you will see that it creates only mz. Okay, it creates a positive mz, but it's not always easy to see. So I know that this one, it creates a positive moment along the z direction. Okay, and this one, it will create a moment along the x direction, and this one, it will create a moment along the minus x direction if you use your right hand rule. Okay, so again, four fingers along this line, and then so this is the center, you just curve it around. Okay, but it might be difficult for some of you to see. So what you can do is you can always use this formula. Okay, so from the centroid of your cross section, whenever you cut it, and then you can write is equal to my moment is equal to r cross f. Okay, and as long as you can find the distance from here to, for example, point D, okay, so you can find your r, and then you can just cross them with f, and then whatever you get, okay, and then you can group them. So you have I, j, and k, these are the unit vectors, and the values before them, they will be your moment. So it will be mx times I plus my times j plus mz times k. Okay, and so in order to show it, so what we have is, so for the first case, I will also show it. So for the forces, you just carry them. Okay, so I have this 30 kilonewton, it goes to minus x. Okay, so that's why I have Vx is equal to minus 30. I have 50 kilonewton, it goes along the y direction, so I have my P is equal to 50, or you can say Fy. And I have this force, it goes to minus z, so that's why I have this one. Okay, and then you can find your Mx. Okay, so either you can use this equation, or I just told you, I know that this one, 50, it creates a positive moment along the x direction, and the distance is my perpendicular distance, which is equal to 130 times 50. Okay, and this force, if you use your right hand rule, it creates a negative moment along the x direction, and it's equal to 200 millimeter times 75 kilonewton. Okay, so it's my positive, negative, and then this is the effect. Okay, and I don't have any moment along the y direction, and if you look at mz, so this one, it creates a moment along the z direction. Okay, and it's equal to this distance, 100 millimeter times 30 kilonewton. Okay, and couple of things. So if you have a force, okay, for example this one, and if it goes through this line, so if it goes through this y-axis, it will never create a moment along y-axis. Okay, and also it will never create a moment which is parallel to that axis. So since this is x-axis and it's parallel to x, it doesn't create a moment along the x direction, and since it goes through the y-axis, it does not create a moment along the y-axis. Okay, and this one, it is parallel to z, so it does not create any moment along the z-axis, and it goes through y. Okay, and this one, it goes through z-axis, so it does not create any moment along the z-axis, and it's parallel to y. So if it goes through one axis, or if it is parallel, it does not create any moment along that axis. Okay, but eventually, so if you can find them, and if you plot them there, so I will have mz. Okay, I will have an mx. I will have this normal force, and I will have this shear forces. I have Vz, and I have Vx. Okay, and here, so they plot the, since they know the directions, they just put the values, so I know which way they go. Okay, all right, and after that, so for example, what I want to do is, now I need to find their effect at point H. Okay, and in order to do that, so what I see here is, so I have a moment. So for example, this, it will create a normal stress, so I need my I. Okay, and what I also see is, so I have this Vx. This Vx does not create any shear stress, because if you look at here, this is the top surface with respect to Vx. Okay, but since I have Vz, it creates a shear stress, so I need to use Vq over It. Okay, at point H. So I need couple of information. So I need to find the area, because I will use P over A. Okay, and since I have these two moments, so I have Mx and I have Mz, and both of them, they will create normal stress, so I need Ix and I need Iz. Okay, and so these are the things that you need to calculate before you move. Okay, all right, so let's look at this one first. Let's look at the normal stresses. Okay, so when you look at this beam, okay, and this is the centroid, so I have an Mz and I have an Mx going this way. Okay, all right, so then I need to find what are their effect at point H. So I need to find what are my normal stresses. Okay, and so what I know is I have a normal force, which is P over A. Okay, so since P is positive, it will create tension. Okay, and then I have Mz going this way. Okay, and now what I will do is, so I will, instead of using the equation, I will look at each moment. Okay, sorry, this is Mx. Sorry, let me go back. Yes. So if I look at the cross section, okay, so, and I'm looking at point C, so what I have is, I have Mx and I have Mz, and then plus I also have a normal force. So these three, they will create my normal stresses, and what I can write is, this is the equation that I can write. So my I will have a normal stress due to P, Mz, and Mx. And rather than using an equation that we got before, what I will do is I will look at each of them separately and I will determine whether I have tension or compression. Okay. So first of all, I know that my P is positive, so which means that my P over A, I will create a tension. So I know my P and A, we just calculated. Okay. And then I have this Mz. Okay. And since it goes this way, okay, so what I need to do is I need to determine whether it creates a tension or compression. And if you use your right hand rule, since it goes downward, so you will see that on this half it creates tension and on this side it creates compression. So it's tension, so it will be equal to mg times the distance from C to this surface, which is A, so it's 0.02 meters. And since I use mg, I need to use my Iz, so I need to use my moment of inertia along the z direction. Okay, and then if I look at here, so this is my Mx. Okay, and since my Mx is this way, so it creates a compression on this side and it creates tension on the bottom side. Okay, and this side is compression, so that's why I will put my minus. Is equal to Mx times B, so the distance from my kind of neutral axis to H, which is 0.0525 meters, and then I need to divide by X. And don't forget, if I use Mx, so I will use moment of inertia along the X direction. If you use Mz, you need to use Iz. And since we calculated all the values before, I just plug it, and what I will end up with is I will end up with 66 megapascal. So due to these two moments and the normal force, I will have 66 megapascal. Okay, and then I will look at my shear, and for shear, so if I had torsion, it might create shear, and then I also have these two forces. Okay, I have Vz and I have Vx. Okay, and for Vx, it does not create any shear stress. I don't have any torsion, so My is equal to 0. So the only thing I left is I have this shear force that might create a shear stress there. And if I look at it, so I have Vz, and I know that it will create a shear stress along this direction. Okay, and so what I need is, since I need to find my shear stress, I will use Vq over It. Okay, and in order to use Vq over It, I need to find the Q above H. So I need to Q of this area, A1. Okay, and then since I'm looking at, so my Vz is this direction, so which means that when I use my I will use my Ix. Okay, so this is important. So first of all, you can find your Q, so which is the area above H, okay, times the distance from the centroid of that area to your neutral axis, which is C. Okay, so area is 0.04 times 0.045. Okay, and if you calculate the distance from C to its centroid, you will get this information. So this is your Q. But this is important. If you want to find your shear, so we say Vq over It, but if I use this V, okay, and then I find my Q, so this I, it will be the perpendicular to Z. So since this is X, if I use Vz here, I will use Ix here, okay, and then thickness. So thickness is from here to there, which is 0.04. So this is very important. So for the moment, so these indices are same. If I use Mz, my moment of inertia is Iz, okay? But here they will be different. So I use Vz, so I need to use Ix, okay? So when you use Vq over It, so they will have the different indices, okay? And when you calculate it, so you will find that your shear stress at point H will be equal to 17.52, okay? And so I find my normal stress and I find my shear stress, which means that I can get my maximum stresses. So all I need to do is, so either you can form your Mohr circle, okay, or you can do your shear is equal to your Tmax is equal to R, okay, and it's equal to basically, in this case, so you have normal stress minus the other one is 0, so you have only sigma y, okay, and then you only have one shear, so you can use this formula to find your R, which will be equal to your Tmax, and for your maximum, so it will be equal to half of your sigma, because you don't have any stress on the other direction, okay, so this is average plus R, you will get 70.4, and your sigma mean is equal to your average minus r, which will be equal to minus 7.4. Okay, and after that you can find your principal stresses and etc. But if you do that, so you will get that your maximum shear stress in plane will be equal to 37.4, your other maximum will be equal to 70.4, and your minimum will be equal to minus 7.4, and your principal angle will be equal to 13.98. Okay. Alright, so again, this is how it looks like. So you have sigma y, okay, so this is your normal stress, and this is your shear stress, and in this case your sigma z is equal to 0. So this is why your average is just equal to sigma y over 2. Okay, so that's why sigma y over 2. And this directions and etc. they might change. So sometimes you might even have tau yx. Okay, but in this question you have tau yz, and this direction will be your z direction, and you don't have any stress along the normal stress along the z direction. So that's why OC, so your average is just half of your sigma y. So this is another example of combined loading, and now we have three forces applied at this point and there, and so the cross section is given, so it's 20 by 40 millimeter rectangle, and we want to determine the principal stresses and maximum shearing stress at point H. All right. So first thing is we need to cut the plane where it contains H, and we need to move everything to the centroid. Okay, we are not moving to the H, but we are moving to the centroid of the cross section that we cut. Okay, and first thing is we just move the forces. So if, for example, if you have 3 kilonewton, it goes minus x. We have 0.5 kilonewton, it goes minus y, and we have 25 kilonewton, it goes to minus z. So you just move them down. So this is what you get. So you get minus 2.5 kilonewton, and then we need to find the moments. So this one is, it goes through origin, so this one does not create anything at all, and this one is parallel to y, so it does not create any moment on y, and it also goes through x, so it does not create any moment along x, but it creates a moment along z, and it is this distance times its magnitude, and it goes, if you use your right hand rule, so forefinger going downward, so it will rotate towards minus z. Okay, and this one again, this is parallel to z, so it does not create any moment along z, so it goes through x, does not create any moment along x, but it creates a moment along the y direction. Okay, and if you are not sure, you can always use m is equal to r cross f, and you can find the moments at the centroid, but these are the values you will get. So you will get a my due to this 2.5 kilonewton force. Okay, and then you will get a moment along the minus z. Okay, and so when you look at that, so what you will get is, so these are the forces, I just move all the forces there, and these are the two moments that you create. Okay, and then after that, now we need to determine, since I'm at point H, I need to determine what kind of stresses I might get. Okay, so this is a normal force, so I know that it will create a normal stress, it will create a compressive stress, and here I have 0.5 kilonewton, so, and if it's towards minus y direction, so it goes downward, and since this is top surface, this one will not create any shear stress, and I have 2.5 kilonewton, yes, it will create a shear stress, and it's in the midpoint. And when I look at these two moments, so when you look at this my, and since my h is here at the centroid line, so this force, this moment will not create any stress at point H because it's at the neutral axis. Okay, but this one, it will create a stress, and it's at the top. Okay, so you might need a couple of information. So one of them is area, so you can get the area, and then since I will use mz, I also need iz there. Okay, and the first thing is I need to determine what's my normal stress. So I know that normal force and moments, they create normal stress, and I just told you that my does not create any moment at point, does not create any stress at point H. So which means that I have compressive stress due to this cleavage, and plus I have a tensile stress due to this moment. Okay, so I will suggest you to determine what kind of stresses you will have, and then for example here I have compressive stress, that's why I put minus the absolute value P over A plus mza over iz. Okay, and A is distance from here to there. Okay, and so by this I know that here this normal force, it creates compression, and this moment it creates tension. Okay, alternatively you can also use the formula, because in this case when we get the formula, if you remember, y was going upward and z was horizontal going to the left. So you can also use the formula we generated before, but I highly suggest you to determine whether you will have compression or tension, and then just use absolute values, and if you have compression put minus, and etc. So if you do that, so I have P over A, so it will create a compressive stress, and I have mzy over iz, so it will create a tensile stress. Okay, and if you do that, so this is the stress that you will get. This is a normal stress, which is sigma x in this case, because this is my x-axis at point H. Okay. And then for shear, I told you that this one, the Vy does not create any shear. The only shear stress will be created will be according to Vz. And since this is rectangular, so don't forget that for rectangular cross section, if you are looking at the maximum stress which happens in this line where H is, I can use this formula. So this is only for rectangular cross section, okay, where I'm trying to find my maximum shear stress, which is where H is. Okay, so at the midplane. So if you do that, is 3 over 2 Vg over A, so I don't need to use Vq over It. So if you want, you can do it, but you will get the same answer. And if you do that, you will find that the shear is 4.6875 megapascal. So if you draw it, so I have this normal stress, which we find at H, and then I have this shear stress, and then on this axis, so which will be my sigma z, I don't have any stress, I don't have any normal stress along the z direction. So in this class, the only time that we might have a perpendicular stress is for pressurized vessels. Okay, if the question does not involve any pressurized pipe or vessel, so you will always have the other one equal to 0. And then after that, I need to find my maximum. So my maximum stress is equal to my average plus R. So average is equal to 1 over 2 sigma h, because I don't have anything on the perpendicular direction. And R is equal to average square plus your shear square. So this is your R. So if you want to find the maximum, you just add them. If you want to find the minimum, you just subtract R from average. Okay, and then you can find the planes where they are maximum by using the equation we there. And we know that our maximum shear stress is equal to R. And in this case, since A is positive and B is negative, I know that this is absolute maximum. So it's also, this is both in plane and out of plane maximums. Okay, so that's it. After you find normal stress and shear stress, you just use the formula for principal stresses, and you get your maximum stress, minimum stress. You can get the angle, and you can also get what's your maximum shear stress. So here is another example about combined loadings, and this time we have a pipe, and it has an inner diameter of 36 millimeter and outer diameter of 42 millimeters. And at point H, we want to determine the normal and shearing stresses. Okay, and what we will do is we will do something similar. So we will cut at a section where it contains H, and then we will move all these forces and their effects to the centroid first. Okay. All right. So when we cut at H, what you will see here is, so I have these two forces. They have the same magnitude but opposite direction. So which means that basically they create a couple. And since this one goes counterclockwise, it will create a moment along the minus x direction. Okay. And if you look at this one, so if you move it there, what you will see here is, so this is parallel to x, so it will not create any moment along the x, but it will create a moment along the z, so it will be a torsion. Plus, it will also create a moment along the y-axis. Okay. And if you find them, so they two cancel each other, so there is no net effect at the centroid where h is. Okay. But when you move this force, so it's along the x direction, so I have Vx. So for forces, P is equal to 0, which is basically Fz. and then fx is equal to vx and fy is equal to 0. Okay, and again at Mmax we have this couple created by this two forces. Okay, and my I have equal to 100 times the distance from here to there, so it's 250. Okay, and for mz, which is the torsion, I have 225 times 100. Okay, and if you use your right hand rule, so it rotates it. If you look at from this side, it rotates it along the minus z direction, so that's why you have minus, and it also rotates it plus my direction, so that's why you have my direction. If you are not sure, what you can write is, you can write this r from h to where you apply this 100 Newton, and then you can just do the cross product. Okay, but if you do that, this is how it will look like. So I will have one force along the x direction. Okay, I have one moment along y direction. I will have another moment x direction minus x direction, plus I have this torsion. Okay, and then this is important because now I'm looking at point H, so I need to know what kind of shears or normal stresses I can get. Okay, so since this is in the mid plane, so I know that I will have this 100 Newton, it will create a shear stress at point H. Okay, and since I'm here, so I know that this moment, which is my, it will not create any normal stress. Okay, this moment it will create the maximum normal stress mc over I. Okay, and then torsion, it will also create a shear stress tc over j. Okay, so in order to find all stresses, I need some section properties. So I can find the outer radius c0, I can find the inner radius, I can find the area, and for circular cross section, this is j and this is I. Okay, I is just half of j. So if I do that, so I can get all these properties. And also, so this is important for you to know. So if I apply a shear force, okay, and for half pipe, so if you want to find the Q where the H is at the mid of the circle, so what you can use is you can use this formula. Okay, so Q of this line, okay, in the middle is equal to 2 over 3 c0 cube minus ci cube. Okay, so if this was a solid circle, you can just use 2 over 3 c to the cube. Okay, so it might help you a little bit. So this is so if you want to find a shear stress of circular cross section at the midplane, you can use this formula for Q. Okay. So after that, what I need to do is just find my normal stress. And again, since I don't have normal force, so I will only have one normal stress due to this moment along the x direction. Okay, and it goes to minus x direction, and I know that at the end I will get compression. So if you write it, so this is your equation for normal stress, you will get compression, mxc, and I, so since it's circular, your ix or iz, they are all, or iy, they're all same, so you just have one I. And then if you write it, so this is how you get your sigma. Okay, but for shear we need to be a little bit careful. Okay, so here I know that my shear stress will be along the x direction. Okay, on this case, which is due to vq over it. Okay, and then you also have this torsion. Since my torsion is going clockwise, I will also have a shear stress along the x direction. So that's why when you write your shear stress, it will be equal to tc over j. This is due to torsion, and this is vxq divided by it, and this is due to your shear force. Okay, and we find all the things. So I know what's my torque, I know what's my c, I know what's my j, q we just calculated, again I, and the thickness is basically your diameter, and we also find vx. So if you do that, you will find that your normal stress is minus 20.2, and then your shear stress is equal to 2.82 megapascal. Okay, so basically this is how it would look like. Okay, so if this is your x direction, so you have a compression, and then you have this shear. Okay, and then in this question they didn't ask, but if they ask you, then you can use Mohr circle, or you can use average plus r to find your maximum and also your minimum stresses. So this is another example again for combined loading, and this time I have a rectangular cross section and we applied 3 forces and we want to find the normal and shearing stresses at point A, B and C. And the first thing we will do is we will cut where at the plane where it contains this points, and then we will move all these 3 forces to the centroid. So when we do that, so we will move everything to our centroid. So I have 50 kips, so which I will have this P, okay, and I have 2 kips, it goes to this direction, VZ, and I have 6 kips, it goes to this direction, which is Vx, okay. And here I'm putting the directions, I'm not, and then so since I already put the directions, I'm not going to use the minuses. So it's up to you. Either you can use the positive direction and put minuses, or if you show it on your element which way they go, you can use the values that you have. Okay. So my P is 50 kips, it's with compression. Actually my VZ is along the minus Z direction and my Vx is along the minus X direction. Okay. And when I look at this, since this one it goes through origin, so it does not create any moment. Okay. And this one, so it is along the Z direction, okay. So this is why it does not create any moment along the Z direction, and it passes through your y-axis, so it also does not create any moment on y-axis, but it creates a moment along the x direction. So I will have an Mx, okay. And since it goes this way, it will create a moment along the minus x direction, or you can just show it the direction, okay. And it will be equal to this distance, which is 10.5 times its magnitude, which is 2 kips, okay. And then I also have this force, so this is parallel to the x direction and it passes through y, so it does not create any moment on x and y axes, but it creates a moment along the z direction, okay. And since it goes this way, it creates a moment along the minus z direction. So, and its magnitude is, so the distance from here to there, okay, times its magnitude. And don't forget that when you take the moment, you can take a moment along any point towards the direction of the force. So I don't need to always find like arma here, but I can find, as long as I know where it passes through, I can take any point along its direction, okay. So these are the positive values because I showed the directions there. And next is I need to determine my stresses at A, B and C. So they're all on this side, okay. So one thing you will realize is, so when you look at your stresses, so for normal stresses, so which one creates a normal stress? So P always creates moment stress, a normal stress. And since this is in compressive force, I know that I will get a compressive stress due to P, okay. And then if you look at an arbitrary point here, so what you will realize is, so your moment is this direction, so it will create tension, okay. And plus your MZ is also going this direction, so it will also create tension. So both of them, they will create tension. So this is why when I write my normal stress, so I know that I will get compressive stress due to my P, and both of this, due to these moments, I will get tensile stress. And don't forget, since when I use MZ, I need to use IZ, and when I use MX, I need to use IX, and the rest is the distances. So I can write this equation, okay. So I don't need to worry whether they are minus or not. And then when you look at for shear, so we don't have torsion, so we don't have any shear stress due to torsion, but we have these 2 shear forces, okay. But since my ABC are on this line, so this, if in respect to VZ, so they're on the kind of top surface, so they will, this VZ will not create any shear stress, but Vx it might create, okay. So this is why when you find your shear, it will be equal to Vxq Iz times T. And don't forget, if you use Vx, you use Iz, okay. So these are different, V and moment of inertia, and for normal stress they have the same indices, okay. So due to that, I need to know a couple of section properties, so I can find my area, plus I also find my Ix. So Ix is here, so which means that this is my base and this is my height, okay. And Iz is along this direction, which means that this is my base and this is my height, okay. So don't forget which one is which. So make sure that you can find this moment of inertia correctly, okay. Alright, so then what I will do is first I will look at point A where it's in the middle, okay, at this point. So in order for me to find my stresses, so what I also need to know is I need to know my Q, okay. And so if you want to find Q, basically you need to know the area above it or below your point, which is this one, okay. So its area is 1.8 times 2.4, and then I need to find the distance from its centroid to my neutral axis, which is this, okay. Or in this case, this is special because it's a rectangular. I can also use 3/2 V divided by area, but just for this one, okay. Alright, and then you can also write the coordinates of this point. So it's along the x is 0, and you can also write z is equal to 0.9 in this case, so the location of your point, okay. So if you find your normal stress, so I have compressive stress, and then I have a tensile stress due to my moment Mx, okay. And if you calculate it, this is the stress, that normal stress you get. And then for shear, we use Vq over It. So so I know what's my V, we just calculated Q, so this is the I value, and this is T. So since I know all the information, so this is Iz, don't forget, so you can get your shear also, okay. So I have normal stress of 231, and I have shear stress of 1.042. Next is we'll look at point B. So point B is here, okay, at this point, so it's somewhere here, okay. So which means that when you look at it, okay, and if you want to, so my B is here, so if you want to find your Q, so I need to use the area, this area, so it's a little bit smaller, half of this, okay, and then I need to multiply with the centroid of that area to my neutral axis. And then, so this case, so when you write your stress, now I will have compressive stress due to compressive force, okay. But now since I'm at this point, I will also get a stress due to my due to the other moment too. So both of them, so Mz, okay. So it, in the previous case, since I was here at the neutral axis, I didn't have any moment due to Mz, but now I also have a moment due to Mz, a normal stress due to Mz. And this is my normal stress due to Mx, okay. So you just plug the numbers and you get your normal stress, so it increased because I have also a component, I have additional moments, okay. And when you look at this, so this are same, okay, and these two are same, so and they will, so since I'm on this plane, so this values, they will be same for the point C as well, but this stress is changing, so I'm an additional one. And then if you find your T, so again I can use Vq over It, and since I'm looking at this point, I expect something smaller, so that's why I get a little bit lower, because my Q is smaller, okay. And then lastly we will look at point C, so which is at the corner, okay, and you can write the coordinates, so you know what's X and Z. And then since I'm at this point, so what I can write is so my Q is 0 because there is no area under that, okay, so I will not have any shear stress, but my normal stress, so the first term is same, second one is larger, and then the third value is same. So when you calculate it, this is your stress and your shear is equal to 0. So here is another example, again combined loading, and I have a circular cross section. So this time I have solid cast iron bracket as shown, and it has a diameter of 0.8 inch, and I want to determine the principal stresses and the maximum shear stress at point H and K, and the loadings are given, okay. Alright, so we will do the same thing, we will just cut at the cross section where it contains H and K, and then we will move these two forces to the centroid and also their effects, okay. And when I do that, so I will use, again, I need to find my three forces and I need to find my three moments. And when I look at this, so now my normal is Z direction, so which means that the forces on X and Y direction, they will be my shear forces, and the force on Z direction will be my normal forces. And when I look at the moments, so the moment along the Z, it will be my torsion. So when I move this, so since it already goes through the centroid, it does not create any moment at all, okay? But this force, it will create a moment along the z direction, okay? Actually, it will go to minus z direction, plus it will also create a moment along the y direction. Sorry. It will also create a moment along the x direction. And since this is along the y direction, it will not create any moment along the y direction. Okay. So if I find it, so I just move this force, and it's just P, it will be equal to 25,000 pounds. And since this is along the minus direction, my Vy will be equal to minus 600 pounds, okay? And my moment, it will be along the x direction, it will be equal to my distance from here to the centroid, okay? Which is equal to 3.5 minus 1, 2.5 times 600, and same thing for mz. But my mx is, it will rotate like this, so it will be positive. But my mz, which is my torsion, it will be negative. So if I show it, so I have my two forces, okay? And I have one torsion, and I have one moment there, okay? And now I need to figure out my stresses at point H and K, okay? And when I look at this, so this normal force, it will create compression in both points, okay? And I have 600 pounds, and I know that it will not create any shear stress at H, but it will create a shear stress at K, okay? And here I have torsion, so in both points H and K, it will create a shear stress, TC over J. And plus I have this moment, okay? And this moment, it will not create any stress at K, but it will create a stress at H. Okay. And if you look at the section properties, so you can write, you can find the area, you can find the R, you can find the J, okay? And then since this one, it will create a shear stress at K, I need to find my Q, and we just learned that for semicircle, I can use this formula, Q is equal to 2/3 of C cube, okay? All right, so these are my forces and my moments. And at first I will look at point H, okay? So at H I have my stress due to my normal force, and this one, it will also create a moment, okay? So I can write it will be equal to P over A plus MC over I, okay? And P over A, since I have minus already inside that, so it will be compression, and this one it will be tension. So make sure that you know it. If not, you can use the absolute values. So I will have compressive stress due to my normal force, compressive force, plus I will have tension on, since it's on the top, MC over I. Okay. So if you calculate it, this is your normal stress at point H. And for shear, so this 600 pound, it does not create any shear at H. So which means that I only have one equation, TC over J. And we know all the values. So from there, you can get your shear stress at H. And then if you want to find your maximum, so what I need is I need my average and I need my R. So these are the equations you can get. Average is half of sigma H, and this is my R. And if you add them, you will get your maximum. If you subtract, you will get minimum. And if you take the difference between them, you will find your shear stress, okay? And then if you calculate it, these are your values. Since one of them is positive, one of them is negative, I know that this is my absolute maximum shear stress, which is also my maximum shear stress in play. Okay. And then if you look at point K, so this time at point K, so this moment, it does not create any stress because this is at the neutral axis, so which means that I only have compressive stress due to compressive force. Okay, and we find it here. And now if you look at the shear stresses, so 600 pounds, it creates a shear stress going downward, and this torsion, it also creates a shear stress going downward, so which means that I need to add them. So this is why I will write TC over J plus VQ over IT. So we find all the parameters there, so when you calculate it, you will get this large shear stress. Okay, and then you can determine what's your average and what's your R, okay? And then you can write again our equations. And if you do that, these are the results. So you will get that your maximum normal stress is 14.21 ksi, your minimum is minus 1918 ksi, and then you can also find your maximum shear stress by using this equation, which is also equal to R. So this is how we solve our combined loading. So important thing is carry all the forces to the centroid, not to the point where you want to find your stresses. So write your forces, write your moments, and when you want to find your stresses, look at there and figure out which ones creates stresses, okay? And your normal force and your moments, two moments, it will create normal stress, and your torsion and shear forces, they will create shear stress.